This is Feng Wang from home, and I hope at this time everybody has a warm and a safe place. Uh, Unfortunately, there are more and more coronavirus cases are confirmed in Pennsylvania and other states. However, we do have a very good news today. I just heard this a few hours from our president, Mr. Trump. So there is a very promising candidate, which is actually an organic molecules that can be used to treat coronavirus the patient. This is the structure right after work from PPG. I came home and find the structure of this organic molecule. It's called a hydroxychloroquine. My pronunciation probably not correct, but that doesn't matter. This is chlorine part. You see this chloro. This is hydroxy, and this part is actually the quine part. So whenever I saw this structure, I thought, oh, this is aromatic molecule. So that's actually the molecule. So we are learning right now. So I want to check the real 3D structure of this hydroxychloroquine. Then I used our software, the Marvin Stretch, to draw the 3D structure. First I draw the 2D structure, then I turn into 3D structure with the Marvin space. This is the result I have. I just want to check one of the requirement for the aromatic molecule, so that the ring, you say this is the ring. The ring has to be a pure planar structure. You know, it is a planar structure. So I can share with you, again, I can share with you one more time. This is a aromatic molecule. We learned recently we have to meet 4 requirements for aromatic molecules. I would like to invite you to do the similar thing, draw the 2D structure and turn it into 3D structure, then count how many electrons in the ring and decide or practice this new molecule, the promising molecules. Is actually aromatic molecules. Well, I told you this many times before. Organic chemistry or chemistry is a very fundamental thing for our daily life. This is one more time you see a good example. If we develop a good organic molecule, that can really help people, not only in this country, but worldwide. All right, now let's go back to our organic chemistry. I don't forget the promise I made to you. I want to share more examples with you, but I also need your help. I want you to propose me the examples you want to share with your team and the whole class. The first example actually was proposed by Phil's team. Basically, it's homework 52C of chapter 14, I believe. So we want to make a target molecule. This is the target of the molecule we want to make. So obviously, this molecule is a ring structure. Whenever you see a ring structure, think about it, Diels-Alder reaction. That's one of the only few organic reactions that can make a ring structure. Well, if we just look at the structure and thinking really hard, it's probably really hard to figure out what the starting molecules to make this organic target compound. So my trick I want to share with you is to particularly label the carbons in the 6 membrane. because we know the fundamental. This is the fundamental, the very simple Diels-Alder reaction. Diels-Alder reaction gives us a 6 membrane with a carbon-carbon double bond here. So just to label each carbons from here 1, 2, 3, 6, 5, 4. And then comparing this structure with this structure. And again, label the 6 carbons in the target molecule. 1, 2. See, there is a sigma bond, pi bond between 1, 2. It's a carbon-carbon double bond. 1, 2, 3, 4, 5, 6. You know, just a circle the ring from 1, 2, 3, 4, 5, 6. Now let's decide 1, 2. 1, 2. This is 1, 2. Just, you know, 2 carbons connected by a sigma bond. Then whenever we decided 1, 2, it's easy to decide 3 and 6 because 1 connect to 3. No, 1 connect to 6. 2 connected to 3. So there is a pi bond. The pi bond will be formed during Diels-Alder reaction. All right, in this structure, you see between 3, 6 carbon, there is also a bridge carbon here. So we have to draw in the bridge carbon between 3 and 6. See, it's a carbon here, just connected to 6 and 3. 6 and 3. This bridge, the carbon probably not involved in the Diels-Alder reaction. Then 4, 5. This is a 4 and a 5. So on number 4, 4 and 5 basically is alkene. It's a carbon-carbon double bond with the other atoms or groups attached to these 2 carbon. So if we take a look at number 4 here, number 4 actually attached to hydrogen here. So the raw molecules, the starting molecules, will have 2 hydrogens here. So number 5 actually connected to 2 things. One is chlorine atom. So number 5, chlorine atom. A second thing is basically an ester group. We just need draw in. This is number 5, draw in the ester group. So this is a trick I want to share with you, and I think if we do the if we label all the carbons in the 6 membrane, that would help, at least that would help me to decide what kind of material to make Diels-Alder product. Or if we are given, you know, this is the molecules, I want to do Diels-Alder reaction, what kind of structure we will have. So I would suggest you know, if you don't like this structure, you can just draw structures like this. Then draw in the rest of thing like a 3 and a 6. There is a bridge, you can draw in bridge like this, 3 from here to here, then back to 6. This is a bridge thing. 5, 5, 4, you have 2 hydrogens, you don't have to draw in 5, you just draw chlorine here and an ester here. So it does not have to be the exact like this for the 6 membrane, but people normally draw Diels-Alder reaction structures with the bridge carbon like this. All right, then let's take a look of more aromatic reactions. This is the third and the final lecture of chapter 16. So in this part, we are going to some new reactions from aromatic compound. A very important reaction is called a nucleophilic aromatic substitution. In the first lecture and second lecture, we learned a lot about electrophilic aromatic substitution. Electrophilic substitution reaction, the key point is how you generate the new electrophile. It's something that bears positive charge. However, some cases there is no positive charge molecules. It's hard to generate electrophile, so there is no electrophilic aromatic substitution reaction. Instead, we have a strong nucleophile. A nucleophile basically something bear a negative charge or bear one or multiple lone pairs of electrons, and they want to share with others. So if we have a proper aromatic molecule, say, remember I have to say it has to be a proper. Proper means here in this case it has to have a very, very good leaving group. The halogen. We know from chapter 7, I believe halogen, they are very, very good leaving groups. So they are willing to leave instead for nucleophiles to join in to do the substitution reaction. So again, at least two requirements: a very strong nucleophile and a very good leaving group. So third one, I don't want to say a requirement, but normally helps nucleophilic aromatic substitution reaction. Basically, we don't have to, but it's very helpful to have an electron withdrawing group. So again, benzene ring has 6 electrons here. It's hard for a nucleophile the electrons to join the benzene ring. But if we have a strong electron withdrawing group, it's going to pull the 6 electrons away from this benzene ring, which really help the nucleophile's electron to join this carbon, and for the very good leaving group of halogen to leave this benzene to form the substituted product. This is the structure, and this is the fundamental of the nucleophilic aromatic substitution reaction. Again, the key point is nucleophile, strong nucleophile, and a very good leaving group. There are two proposed mechanisms for this nucleophilic aromatic substitution reaction. The first one is called addition elimination or elimination addition. So again, I'm not a big fan of the names, but I really want you to understand the fundamental things of the nucleophilic aromatic substitution reaction. Alright, here is the addition-elimination reaction. We actually have two molecules, two aromatic molecules, chloronitrobenzene. So the difference here is the position of the nitro group, either the antipara position relative to chlorine or at the meta position. So whenever the nucleophile attack this carbon here, again, this is a very strong electron withdrawing group. So to help the nucleophile to attack this carbon. So if the nucleophile attack this carbon, we can have different resonance structures. Basically, we generate the negative charge on the benzene ring. The negative charge could be here, could be here, could be here. It's not evenly distributed on 6 carbon. It's on this position, and this position. We know, and this is particularly interesting because you see here this carbon bears a negative charge, and this nitrogen bears the positive charge. So we can see, oh, okay, this carbon has a very, very good neighbors because I have a negative, you have a positive. So a good neighbor means that this resonance structure is very, very stable, more stable than this one and than this one. However, if we have the nitro group at the meta position, we can also draw the different resonance structure, but to delocalize the negative charge. The negative charge could be here, or here, or here, third position. 9 of these structures which has the good neighboring effect like this one, negative, positive, they're linked together. So again, this resonance structure gives the structure that intermediate much stable state. So in other words, if the very strong electron withdrawing group and the pair position, or sometimes at the pair ortho position, they have the similar effect, which helps the nucleophilic substitutions reactions a lot. But if the group at the meta position, actually does not help much. Another mechanism for the nucleophilic substitution reaction is called an elimination addition reaction. So this is an example. In this case, we need a very, very, very strong base. So chlorotoluene, and with the benzene with the methyl groups is called toluene. This product called toluene. So this part is chlorotoluene. React with ammonia and sodium amide. So we are going to have two substituted product. The chlorine either substituted at its position here, or the chlorine left, but the substitution occurs at the neighboring carbon, neighboring of this chlorine. You see this position. So why this happen? So let's take a look of the mechanism of the elimination addition of nucleophilic substitution reaction. So again, chlorine is a very good leaving group. Sodium amide is very, very one of the strongest base. Actually, the first step is the formation of alkyne, like alkyne, a carbon-carbon triple bond. This is what we learned in chapter, I believe chapter 8. So very strong base to do the elimination reaction to form an alkyne carbon-carbon triple bond. The next step, we have a 2-pi bond here, and we have ammonia. In the reaction, the ammonia next step will attack this triple bond, one of the pi bond, to form a substituted product, toluene with amine substituent here. So when the amine reacted to the triple bond, actually the amine. When amide react with the triple bond here, actually the amide can attack this carbon, or the amide can attack this carbon. These two carbons basically they are very, I don't want to say they are equal, but they are very, very similar in physical and chemical property. So the very strong base can attack one of them. So that's why we have a substituent either ends at this position, basically the chlorine position, or its neighboring. That's why it's in the neighbor carbon is because of the formation of this alkyne carbon-carbon triple bond. It never happens at this carbon or this carbon. So it has to be the neighboring carbon, either here or there. Here, basically they are the same. That's why the nucleophilic substitution reaction with the elimination, first step elimination to form a triple bond, addition mechanism. So the substituent either enter the halogen position or enter the neighboring carbon's position. All right, I want to take a break at this moment for you and for me. Then I will see you later.